So hi, I'm Eric,
I'm Michael.
I'm Austin. I'm Brent.
and this is Team Papa's presentation on our asset tracking system.
All right, so basically our system is we need to track the weight and the tags of the bins. So it's implemented so that when a bin is put on the scale, we read the tag in to ID the bin number, and we link the scale data with the ID number, and we output that over XP to a computer that's monitored at the winery, and also it's stored on an SD card inside the module itself. And yeah, this is
okay. So a little system overview. So what we've been doing is we've been testing out different RFID readers. We've been trying to see which one would be best for our application. What we've been doing is looking into just currently like hobbyist readers, ones that are available in most electronic stores. And what we did was we just tested on these range, the functionality, and everything. So we did that. We centered our design around making sure that at the winery we didn't have to worry about it being a huge hassle for them to have to deal with this RFID reader. You know, it has an antenna with it and everything, so we don't want this to be a huge impact on the winery. We want to make sure it's as low form as possible. So we've also been testing out battery life a lot, and we have collected some data on that we'll show you in a bit. And so we'll talk a little bit more about that.
This is our alpha board layout. We have a lot of different components on here compressed into a small space, but what we basically have is our voltage regulation via boost converters, 12 volts to power our scale display, and 5 volts for the circuitry on the board, and the XB and RFID, which are off-board, connected to those headers on the far right side. We have a reset button, we have a mini USB port for charging, and a battery connector for our lithium-ion battery. We also have an RS-232 driver and receiver, which is for interfacing with the scale display, just converting the RS-232 signal to TTL logic, which we interface with using UI.
So we have a little bit of a GUI demonstration we thought we'd show, and so I can sign in. Oh, wait, I think I'm signed in as Unique. That's not right. So if I click on that again, I'll sign in.
Is it like over 18 or something?
No.
Default settings.
You're gonna hate me. I have to get a text message from my phone.
Oh really?
Yes. Shit.
Don't forget your password.
Yeah, that's what if you have a laptop that you can just plug it in and.
I care about security. I care about security.
They sign in box.
1 second.
that's hilarious.
I didn't expect it to do this.
As everybody's still checking their YouTube videos, visually
I haven't got it.
How about just keep going and we'll pull it up at
Okay,
the end. Yeah.
fair enough. Sorry about that. I guess I'll just get the next one.
No,
I'm not gonna try it. So, Michael, you can.
So what we have here is a sideways picture of the, we have a boost converter. We have a 12 volt boost and a 5 volt boost converter running off of the 3.7 volt LiPo battery. So this is a readout of the 12 volt boost being measured right at the output of the boost, and then again on the 5 volt boost. So this is our boost circuit that we're using, configuration. We're using a standard 3.7 volt LiPo battery like I said earlier. We're using the Texas Instruments boost converter. It's pretty standard configuration. We have, this is our charge circuit IC that's taking a 5 volt USB and charging the battery. We've got 2 lights. We have one light that says that the power's good, and then 1 light indicating that it's charged. I think we'll show that. No,
It's eventually more power regulation.
So this is the schematics for the 5-volt and 12-volt boost circuits. They're basically identical circuits. The only difference are the values of the resistors and the inductors. So these are standard values based off of the data sheet for these typical voltages. Not a lot of configuration.
So we're interfacing with all of our peripherals via UART. That is the communication mode that is used for our RFID module, scale display, and for XP communication to a wireless point.
Alright, so one of the first sensors we looked at was the ID20LA as an RFID reader. And its main thing was that we could run it at either 3.3 or 5 volts, so that was really good. So we didn't need to step up the voltage from our battery. But the main drawback to it was its read range wasn't nearly as close to 180 millimeters as we thought it would be. It was probably around like 8 centimeters, like 80 millimeters. And so that was a big drawback because we need the vents to be further away. So that way they're not bumping into the sensor all the time, because that could cause damage to the whole module. And so that was one of the reasons that we decided not to go with the ID20LA.
So the next one we chose was a parallaxis RFID reader. It had a greater range on it, but it came at a cost of increasing the voltage and also increasing the current consumption. So it increased our power consumption a lot, and that was a bit of an issue. It took a lot of power regulation to make sure that we can actually operate that. It was a pretty, I would say it was a pretty easy setup to implement. This one also does read and write capabilities, so it has that capability to do that. And it had a flat antenna, which was attractive, mainly because we can put it on a flat surface. So what we decided on was the ThinkMagic ME5E. It's a bit more expensive than the two sensors we've shown. It's about $300 for the sensor, and the reason why we chose it was mainly because of a few reasons. Mainly because of its industrial capabilities. Its ISO rating was approved for being used in the industry, as opposed to the other ones. The next one was actually the range it provided. It provided a huge range that we could regulate whether we wanted to decrease it or not. It had very fast timing and for reading tags, along with a good power rating for our application.
So our goals for the beta, we are upgrading our battery. We're thinking about switching to 12-volt sealed lead acid battery or some other chemistry, but just a higher voltage, so we don't need to boost up our voltage levels nearly as much. We're using a PSOC 5 instead of PSOC 4 because we're going to also need to interface to a micro SD card for offline data storage, and we just can't do that with the PSOC 4's communication BLS. Improved time aspect and error checking the data, that's just more processing on the data we're receiving. Determining optimal field test range, that comes with testing the new RFID reader to make sure that the bins are able to be read effectively while also protecting the electronics from any injury. Implementing the micro SD card for local data storage and user interfacing potentially with the remote control device that we're thinking about, and also getting this into a small convenient package for the final system implementation.
Let's see if we can get that video going. How do I escape? Okay. Don't steal my code. Okay.
Hi, this is Eric and Bart with the bin tracking system.
Currently, what you're seeing here is our GUI that we have working with our alpha design using PSOC 4. We're using a parallaxis RFID sensor, and it came with 2 tags that we're going to show today. The plan is we're going to press the start button to show the weight and the time along with the tag ID associated to it. Basically, the GUI is going to be acting as a remote. So now we're going to actually start that with one of our tags. So please. It's going to start. That's the first. So what you see here is the gross weight. Right now we don't have it hooked up to the actual weight. We have it hooked up to the display, and the display does put out something. It puts out just the gross weight. There's a tag associated to it as well, and you see the time down there, so that timestamps everything. Right now we're going to be switching the tags, and as you notice, the tags should change. Both the tag name, the picture, and all will be changing in just a bit. They all have very unique IDs that we can read and write to. So, and all of this is actually stored in a data file that we have going on in our SD card. So we are able to data track everything, log it, timestamp everything, and keep it all local. So this is our data log file that we have currently stored on our SD card. It's just a template, or of the work that we will be saving. It has the tare weight, the scale weight. We'll have also the tag, and finally the time. So the beauty of this is that while it is stored on the SD card, it's easy to pull off. And in case wireless does go down, we can retrieve the data still. And we have quite a bit of data that runs on for over 2.5 to 3 hours. Lab GUI with our tags and everything, and right now we're demonstrating is the functionality of it. You can see the tag changes when you change the type of tag we use. Every time the light changes from green to red, it indicates that there's a reading being performed. Here we have our current setup. We have the XB plugged into our prototyping PSOC along with our SD card, followed by interfacing with the scale. Currently what you see on the GUI is an 8-pound gross weight, which is actually what you can see on the display over here. That's indicating accurate read. Okay.
Yeah, sure.
All right, we have one more quick video, if it works.
We know you're.
Oh, okay.
Should share it later?
I think share it later.
Sorry.
Yeah.